Okay, second lecture for June 3rd. And what we're going to talk about is something I call the force menu. Most of the way I do instruction for this class fits fairly well in some textbook somewhere, which is to say, not every textbook is slightly different, but this is a subject of material that's been taught for many decades and more, centuries really. And if you pick up a mechanics textbook from the 1950s, you compare it to one from 2020, they won't look that different. But occasionally I stumble on a pedagogical device that I think is really extra helpful for students. And even though if it's not in the textbook, I think it's useful enough for students to use. I'm going to advocate it for its use. And that device I'm going to call the force menu. And the idea here is that students, how can I put it? The nature of Newton's second law problems is that you look at a system and you try to infer what forces are being applied to whatever bodies are in that system. And then once you inferred that, you apply Newton's second law. Usually the inference process involves setting up something called a free body diagram, or sometimes it's called a force diagram, but the exercise involves inferring what forces are coming into play. And what I found is that students who are new to the process often, how can I put it, often invent forces that don't exist. So in order to restrain your freedom from choosing and inferring forces that don't exist, I'm going to give you a menu. And I'm going to say any forces that you use in the problems can only come from this menu. If you want to insert a force into a problem and it's not in the menu, then you shouldn't do that. And well, the one exception, if I give you a force, if I say in a problem, here's a new force, then of course, by definition, you should use that force. But if any force that you would infer, in other words, any force that you would be implicit as opposed to explicit to the problem, should only come from this force menu. And if it's not on the menu, you can't use it. That's kind of the idea. I'm basically keeping you out of trouble by inviting you to use this menu. So the menu is actually reproduced on the last page of the Newton's laws review sheet, which is course document number 6. So you might want to find course document number 6 and look at the last page and actually have the menu in front of you so you can compare the details of that versus what I'm doing here. But I just want to sort of run through that menu. So I'm going to give every force will have a name. Every force is going to have a symbol. Every force is either a contact force. Contact is either a contact force, that's not right, but contact force. And every force is either known or it's unknown, or there's something about it that we know or we don't know. We're going to figure out what those are. And for starters, there's only going to be 4 forces. Only 4. 1, 2, 3, 4. Don't invent forces that are on this menu. So the first force is the force of weight. And this is the force that is applied to every body that has mass in the vicinity of the surface of the Earth. And I'm going to use the symbol W. Now, a lot of textbooks say you should use F sub G or whatever. Whatever you learned in the past, take what you learned and set it aside. And for this summer, anytime you use weight, use W with a big arrow on top of it for the symbol for weight. That way, you and I and the graders all know what we're talking about. In other words, even if you learned this stuff from the past and you learned it in a different syntax, this is a college course, you should change to our syntax for consistency. Weight is not a contact force. It does not result from the interaction of two bodies in contact. It's just a force that everybody feels. If I have a piece of chalk and I let it go, it accelerates due to the force of weight on it. And the interesting thing about weight is that we know what the magnitude of the weight is. It's equal to a quantity which is equal to the mass. times that same G, which is the G that came from the free fall stuff. Wow, it's kind of interesting. And this is always true. Now, I'm not going to prove this. I'm not going to derive this, at least not initially. Turns out we can infer this when we understand deeper what gravity is, but we haven't got to that yet. And for now, I'm not going to use the word gravity. I'm going to use the word weight as the force on bodies in the vicinity. And notice that weight and mass are not the same thing. Weight is a force, whereas mass is the amount of stuff. And the weight is equal to m times g. And this is measured in, this is weight, this is mass in units of kilograms, and g, which is an acceleration, meters per second. And the two multiplied together give you a weight in terms of the units of force. And the SI unit of force is a kilogram meter per second squared, which is also known as a Newton. So a 1 kilogram object near the surface of the Earth, where g is equal to 9.81 meters per second, well, let's call that 10, is roughly 10 newtons of weight, okay? And it's known. It's always known. It's all, by the way, it has a direction too. The weight always points down, right? Just like the acceleration. So that's weight. I'm not explaining it. I'm just giving it to you. The next one is called the normal force. The normal force, the word normal does not mean normal as in the opposite of abnormal. It means normal as in the mathematical definition of normal, which where normal is synonymous with the word perpendicular. And normal force is basically a force, any force that's perpendicular to a surface. So I will label the normal force as N. It is a contact force. It can only arise as a result of two surfaces and being in contact. And the easiest way to describe it is that it's a push, and its value is unknown. So a normal force is a force that is basically applied to a body as a result of being in contact with another body, two perpendicular surfaces. So two surfaces together, there's a push perpendicular from one surface to the other, and that's what we call the normal force. It's a push. It's never a pull. It's always a push. And it's always onto the body that's experiencing it. So I say the normal force on me, I mean I experience a push, not a pull. And I'm not talking about the push on somebody else. I'm talking about the push on the body. All right, that's the normal force. And by the way, its value in general is unknown. There's no rule of thumb that will tell you what the normal force is. I'll say this again. There's no rule of thumb that will tell you what the value of the force is. In fact, there's only one way to calculate the normal force, and that is you multiply apply Newton's second law. See, my favorite law, Newton's second law. The only way you can calculate the magnitude of the direct magnitude of this force is to apply the law. You cannot infer its value. You might have seen a lot of problems where the normal force is equal to mg, and if you just put in the normal force is equal to mg, you will get the wrong answer many times, because unless you applied the second law, that's not the right answer. Okay, the next one is what we call tension. And we label it with a capital T. And it's a contact force, yes, because you have to be in contact with a rope or a string or something. And it's simply, the way to think of it is it's simply a pull whose value is unknown. It's a pull whose value is unknown. So if I attach this piece of string or rope to you and I pull on it, unless I tell you, unless you know in advance what the value is, you can't infer its value. You got to figure it out. You got to work it out. Finally, and this is the one that throws everybody, there's friction. The fact that it throws everybody is because you make it harder than it really is. And I'm going to label the force of friction with a little f, with an arrow on it. Yes, this is a contact force. By definition, you can't have friction unless two bodies are in contact with each other. And the way to think of it is this is the definition. It is the force parallel to a surface. Right? So it's basically like the normal force. It results in the contact of two bodies, but instead of the force being perpendicular to the surface, it's the force parallel to the surface. Now, this is the important thing. Any force that results that goes in the direction parallel, any force that's parallel to two surfaces is a friction force. And it doesn't really matter which way it points. As long as it's parallel to the surface, it's friction. That's the definition of friction. Now, is it known? as a rule, friction is unknown. You have no idea what it is. There's an exception to the rule. The exception to the rule is if the two surfaces are sliding, then there's an equation you can use to evaluate the friction in terms of another unknown force, which is the normal force. So only in that special case when two surfaces are sliding across each other, and it turns out that's even a special case because that only applies really under fairly narrow conditions, can you know what the friction is. But in general, you don't know the friction. In general, you don't know the tension. In general, you don't know the normal force. How are you going to figure them out? I mean, you know the weight force, it's mg. That's the good news. But these ones you got to figure out. How are you going to figure them out? There's only one way. Apply Newton's second law. So that's what we'll do for the next 2 or 3 lectures. Talk to you soon. Oh, yes. And if it's not on this menu, don't invent it and don't stick it into your problem. It doesn't belong there.